All right, so now we're going to look at periodic trends for group 7A. Now these are the elements that are closest to the noble gas. So essentially they have one less electron than the nearest noble gas. So for example, fluorine is 1s2, 2p5, 2p6 is a full shell, so it's one short. Chlorine, and again, this is showing the Nobel gas as an abbreviation in brackets. So chlorine is just like a neon atom, but it also has 3s2, 3p5. But again, it's like one short of the next noble gas, which would be argon. Fluorine's one short of being just like a neon atom. So in this case, group 7 elements, they want to gain an electron to get the noble gas configuration of the next noble gas. And since they want to gain electrons, when you gain an electron, electrons are negatively charged, so they form anions with a charge of -1. All right, and then I'm just going to show you here, we don't talk a whole lot about transition metals because they're more complicated, but I just wanted to show you why they're more complicated. So it's a little bit hard to see here, but if you look at chromium and copper are circled. Chromium's got a d orbital that's got 5 electrons, and if you look at the vanadium and manganese, which are before and after it, vanadium's got 3, and manganese has 5, and so it would seem like chromium should have 4, so it'd be 3, 4, 5, right? But chromium actually has 5 because a half full, remember the d orbital holds 10 electrons, half full or 5 is more stable than 4. So the chromium actually has taken 1 out of the s orbital. And same with copper. So you don't need to know these rules, but just know that it's a little bit more complicated for the noble gases, and this is why, because the d orbital, like half full, is more stable than one that's got like 4 or 6 electrons. So for this reason, transition metals are hard to predict their filling order. And then the other elements, which we call the main group elements, which are the ones that are not transition metals or not lanthanides and actinides, they behave a lot more in a more predictable manner, and those are the ones that we're going to be mainly focusing on in this class. All right. And then I'm just going to go through and show periodic trends. And in the next lecture, we're going to talk about this more, trends in the periodic table. But these trends are important because they show us, like, if you just look at where an element is on the table, it can tell you a lot about how that element's going to behave. And the reason it behaves the way it does is because of the electron configuration, which is why I spent all that time going into that incredibly complicated material, because that tells us why matter behaves the way it does. All right, so if we look at the periodic groups, which are columns in the periodic table, it indicates how many electrons are in the outermost shell. So for group 1A, there's 1 electron. For group 2A, there's 2 electrons. And we're going to ignore the transition metals, because again, they're a little bit more complicated. But if we have group 3A, which is also sometimes called group 13, there's 3 electrons, 4 and 4A, 5 and 5A, 6 and 6A, 7 and 7A, and then 8 electrons in 8A. So this is not including the D block. This is just the S and P, which are behave a little bit more nicely than the D. The D, again, the filling is a little bit more complicated. With S and P, it's more straightforward, so it's easier to predict how main group elements are going to act. All right, so if we get, again, the groups show like how many electrons are in the outermost shell. Now we're going to look at the rows. They tell us what principal shell is filling. So if in row 1, the first shell is filling, in row 2, the second shell is filling, and so on. Okay, and in the noble gases, this is where the principal shells are filled. So they have that noble gas configuration that's nice and stable, so they tend not to react. Next thing we're going to talk about are valence electrons, which are defined as electrons that are in the outermost principal shell. So whatever shell that is, for hydrogen, it's going to be the first shell. And then if you're going all up to the francium, it's going to, the valence shell is the 7th shell. So whichever one is the highest shell that has electrons in it. And these are the ones, the valence electrons are very important because these are the ones that are involved in chemical bonding, because they're the ones that are gained or lost. Now remember, the inner shells, and we're ignoring the transition metals, which are a little bit more confusing, but the electrons that are not valence electrons, the ones that are in the inner shells, those shells are completely full, so those are stable and they tend not to react. The only shell that can be partly filled is the outermost shell, and that one since it can often be, unless it's a noble gas, an uneven number of electrons, that is the one that gains or loses electrons, and that's what forms chemical bonds. All right, so how do we know what valence electrons are? It's fairly straightforward. It's the outermost shell, but there's just like one place that I want to make sure that you are aware that it's a little bit confusing. But first of all, we'll talk about the simple example for silicon, for example. We have the valence electrons are in the outermost shell that has electrons, which is shell 3. So that's the valence shell. The one place that's a little bit confusing is if you remember the D subshell fills out of order. So for example, for selenium, we have the D subshell is filling, but then also for the third shell, but we also have electrons in the 4th shell. So the valence electrons are the electrons in the 4th shell, even though the 4s2 fills first and has slightly lower energy than 3d10, it is still considered a valence shell. So you just look at the principal number. And again, notice that in this electron configuration, these are written out of order because they're written in the order of the energy of the shells, but we still have the principal shell is the 4th shell, and that is the valence shell, not the 3d10. Those are not considered valence electrons, those 10 electrons, because they're in shell 3. Okay, so I'm now going to summarize the periodic trends for main group elements. With the exception of helium, the element's group number is equal to the number of valence electrons. So helium's different because it's only got 2 valence electrons, because shell 1 only holds 2 electrons. But for all of the other elements, the group number indicates the number of valence electrons. Now again, this is for main group elements, not the transition metals. So for example, hydrogen is in group 1, it's got 1 valence electron. And then, so does lithium, it's got 1 valence electron in group 1. Beryllium is in group 2 and has 2 valence electrons. Boron is in group 3A and has 3 valence electrons, and so on. So the element's period or row number is equal to the outermost principal quantum number, or the outermost shell, and this is a valence shell. So, for example, again, hydrogen, the valence shell is shell 1. For lithium and boron and carbon and all of those, it's the valence shell is shell 2. For sodium, the shell is valence shell is shell 3, and so on. All right. So for main group non-metals and metalloids, so those are on the right side of the periodic table, the p orbital is filling. For main group metals, the s orbital is filling. All right, so those are the two groups on the left. For the 6 groups on the right, the p orbital is filling. The core or non-valence electrons of a non-noble gas have the same electron configuration as a previous noble gas. For example, chlorine has the same core electron configuration as neon. And if you look at neon and chlorine on your periodic table, you'll see that neon is in the row before chlorine. The neon electron configuration is 1s2, 2s2, 2p6. Now, if we look at chlorine, the 1s2, 2s2, 2p6 is the same. So that's the core electrons, the ones that are not valence, have exactly the same electron configuration as neon. But in addition, chlorine has 7 additional valence electrons, which are in 3s2, 3p5. Now, since this is the only thing that differs between neon, and since it's a lot of work to write out the electron configurations, we can abbreviate the electron configuration of chlorine using the noble gas neon. And to do this, we put the name of the noble gas in brackets, so neon in brackets in this case, and put this where the core electrons would go. So for chlorine, we'd have neon in brackets, 3s2, 3p5. So this is showing you that the thing that's unique about chlorine is that it's got 3s2, 3p5 is the electrons in the third shell, but for the second and first shells, chlorine has exactly the same electron configuration as neon. Okay, so your tables actually show the electron configuration for each element, but it's written in a little bit different abbreviated form, mainly for the purpose of saving space. And so I'll show you what that looks like here. We'll start with helium, which has the electron configuration 1s2 in the way that I told you. On your table, it simply says 2, and what that's telling you is how many electrons are in shell 1. And there's a total of 2 electrons there. Next, we move up to neon, and the electron configuration is 1s2, 2s2, 2p6. On your table, this comes out to 2 electrons in shell 1 and 8 electrons in shell 2. It does not tell you which subshell they're in, just the shell. So that's 2, 8. And there's a total of 10 electrons. Now, if we look at argon, it's 1s2, 2s2, 2p6, 3s2, 3p6. So again, there's 2 in shell 1, and there's 8 in shell 2. That's the maximum that'll fit in these shells. And then we look at the next shell, 3s2, 3p6. That's a total of 8 electrons in shell 3. And then when we add that together, there's a total of 18 electrons, which is also the atomic number of argon. All right, and now we'll look at chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. So again, 2 and 8 are the same because these shells are full, right? They're core shells, so they're going to be completely full, and it's only the last one that's going to change. Now, in this case, the shell 3 has 7 electrons, so that's 2 plus 8 plus 7, or 17 electrons total.